Alright, we're going to get started and discuss another principle of combinatorics, the pigeonhole principle, which is just that if you have n plus 1 things and only n places to put them, then one of those places will have at least 2 things in it, and it's an amazingly simple statement, but its consequences are far-reaching. So let's see your first example. Okay, so let's suppose that we have 9 bell peppers that we've purchased at the store, and that they come in 4 different colors: red, green, orange, and yellow. And that then we know that at least 3 of those peppers have to be the same color. So 9 peppers, 4 colors, then at least 3 of them are the same color. How do we know this? Well, let's suppose that we try and create sort of a worst-case scenario where we try and show that, we try and build up a collection of peppers that contradicts. So we're only going to allow ourselves 2 peppers of each color. Well, then obviously what happens? Here are our 9 slots, 1, 2, 3, 4, 5, 6, 7, 8, 9. So these represent our peppers. These are our pigeonholes in this case, and our pigeons are the colors. So we have 1 that's red and 2 that's red, and now we're not allowed any more red because we're trying to build up a counterexample. Now we have 1 that's green, 2 that's green, and now we're not allowed any more that are green. Likewise, 2 orange and 2 yellow. That only adds up to 8 peppers, and we still have this final slot to fill. So that means we have to fill it with one of the 4 colors we've already used, and so no matter which one we pick, that means that one of our colors has 3 peppers. So there's the demonstration. That's a demonstration of the pigeonhole principle. Okay, the next example is a little bit more complicated. At any party, there are at least 2 people attending who know the exact same number of people. So how do we go about showing this? Well, let's let our people at the party be p sub 1 through p sub n, and those are our party goers, and let f sub 1 through f sub n be the number of friends the number of friends that p sub I has at the party. So if the first person has 3 friends, then f sub 1 is 3. And if the last person, p sub n, has n friends or something, has 6 friends, then f sub n is 6 or something like that. So it's just f sub I is the number of friends at the party that p sub I has. Okay, so again, let's try and build up a counterexample. Let's suppose that no 2 people know the same number of people. That's the same thing as saying that none of the f sub I are equal to each other. So if none of them are equal to each other, then it's possible to arrange them so that we have, bring this down a bit. It's possible to arrange them so that f sub 1 is less than f sub 2, and f sub 2 is less than f sub 3, and so on. Now the order of the subscripts here is somewhat arbitrary, so let's say that we just numbered the subscripts. We just numbered the people and numbered the f's so that this is the case. So we're assuming that no 2 people know the same number of people, and this is the consequence of that assumption, that we can write that f sub 1 is strictly less than f sub 2, is strictly less than f sub 3, and so on, is strictly less than f sub n. Okay, well, we're almost done. Bring this down a bit more. So, well, we know about, everybody has to know, at least one person at the party. So each f sub I has to be greater than or equal to 1 for every I. And we also know that nobody can know all n people at the party because we're not counting the fact that we know ourselves. So that is, the most, if you go to a party with 6 people including yourself, then the greatest number of people that you can know is 5 because you don't count yourself. So what we're saying here is that every f sub I is less than or equal to n sub 1. But this gives us a little contradiction, because what this means is that these n numbers, f sub 1, f sub 2, all the way up through f sub n, have to fit into only n minus 1 slots, 1, 2, 3, all the way to n minus 1, because every f sub I is greater than or equal to 1, and every f sub I is less than or equal to n, but if they're all distinct, if no two are equal, then we have too many numbers. We have too many f sub i's for the number of values that they're allowed to take. So if we try and construct the best possible case, then f sub 1 only knows one person, and f sub 2 only knows two people, and f sub 3 only knows three people, and so on, up to f sub n minus 1, who only knows n minus 1 people, but then we're out of values, and f sub n, there's nothing legal that we can take here. And the only thing that we assumed was that f sub I is not equal to f sub j for any I and j. So, because we have more numbers than there are places to put them, then two of the numbers have to be equal, and that is another example of the pigeonhole principle. Alright, thanks a lot.